Okay, thank you. So is the sound okay? You can hear me with the microphone. So let's continue the talk about non-crossing partition, free probability, and free cumulants. So a quick reminder of what I said yesterday. So the setting is a complex algebra with a unit, a linear form on the algebra A, and which is one on the identity. And we define the free cumulants implicitly as n-linear forms, Rn, which are given by this moment cumulant formula, which is here, which expresses tau of any product of elements, A1, A2, An, as a sum of products of free cumulants the sum is of the non-crossing partitions, and for each non-crossing partition, the product is of the blocks of the partitions. Sorry, I wrote path, but these are the blocks. Okay. And there is an inversion formula which involves the Möbius function on the lattice of non-crossing partitions. Okay, so this was the definition of free cumulants, which is valid in this very general context. So almost no hypothesis on the algebra. And there was this theorem due to Roland-Speicher, which characterizes a certain property of several algebras. So we have this algebra, big algebra A, with tau, and we consider subalgebras, AI, and we say that they are free. Well, there's a definition which was given by Wojciechowski, but which was nice and short, but it was not easy to do computation with it. So the theorem of Roland-Speicher gives another characterization of freeness. The freeness is in terms of these more complicated objects, I mean these free cumulants, and it tells that the AI are free if all mixed cumulants vanish, which means that Rn of A1, An is 0 as soon as you take elements A1, An. Each of them belongs to one of the subalgebras, and there exist at least two subalgebras which are distinct. These indices A1, An, well, as soon as two of them are distinct, we call the cumulant mixed cumulant, then it should vanish. Okay. So how do we use this to make computations? We will see that it will provide us a very natural way of making computation with free probability. So this is the main computation. So you take elements A1, An in some algebra A, B1, Bn in some algebra B, and they assume that A and B are subalgebras which are free in a bigger algebra C, with tau, the linear form. And what we would like to have is a formula for this product. So of A1, B1, A2, B2, etc., An, Bn. So if you remember what I said yesterday, the definition of Wojciechowski is that this is 0 if all the AI are centered. But the problem is that when the A's and the B's are centered. The problem is that when the A's or the B's are, when they are general elements, not centered, then we would like to compute that in terms of just tau evaluated on products of A's or tau evaluated on products of B's. Okay, that's the main problem of that you want to solve. And so what you do, you start to write down the moment cumulant relation. Tau, like that, is the sum of all non-crossing partitions of size 2n, A1, B1, An, Bn. So there are 2n elements, so we need non-crossing partitions of size 2n. And now we use the freeness condition. So if some pi in the sum contains a block which contains an even and an odd number, both of them, then it's a mixed cumulant. So you will get a mixed cumulant in the product, and then R pi is equal to 0. So the sum actually reduces to sum over all non-crossing partitions, which are of the form pi1, pi2, where pi1 has blocks with only odd elements, and pi2 has only blocks with even elements. So this is like I show in this picture here, where you have I put in blue the odd elements, in red the even elements, and I show you a non-crossing partition which has only either blue or red parts, even on odd parts, blocks. Sorry. So we can reduce this sum over all these non-crossing partitions. So it's a formula that involves only here on the left product, evaluation of taus on elements in the algebra A, and here elements in the algebra B. We can slightly improve this formula in the following way. What we notice is that say, if you fix pi1 and sum over all pi2, actually, you see, so suppose pi1 is this for non-crossing partition in blue here, and you are summing over all pi2, actually, you are summing over all pi2 which are smaller than the Creveras complement of pi1. Okay? So in the end, you can use the formula for the moment cumulant formula and see that the formula reduces to this tau indexed by the Creveras complement of pi. So it's a slightly simpler formula because we have cumulants for the A's, but for the B's we compute moments. Okay, so it's slightly, but still it's of course a non-trivial formula. There are many signs. And of course there is a symmetry between A and B. You can do the same for A and B's, and you have the symmetric formula. Okay, so let me look at now the case of one variable. Okay, so for the moment, this will be just about cumulants. There will be no freeness in this case. I will just give you an alternative formula for computing the free cumulants in this case. This will answer a question, I think, by Theo yesterday. So we consider A an element in the algebra A, and its moments, tau of A n. So if tau has some positivity properties and A is a self-adjoint operator, then these are the moments of a probability measure on the real line. And we call this probability measure mu the distribution of A. Okay. So this is, of course, the case you are interested in because you want to apply this to probability theory. Before that, I was very algebraic when describing free cumulants, but in the end, you really want to do probability and compute probability, so you better have some positivity assumption somewhere. So here, in my positivity assumption, I get a probability distribution. Okay. Now you can look at the generating series for the moments and the generating series for the free cumulants here. So I look at Rn, where A is repeated n times. And actually, it's not too difficult to prove using basic properties of non-crossing partition that they satisfy this relation, that M is equal to 1 plus R of Z M of Z. And actually, essentially, from this formula, you can determine the free cumulant by using Lagrange inversion. It's a way of, there are connections between Lagrange inversion and Catalan object like trees or non-crossing partitions or whatever you like. And this is one of the relations of this relation between these objects and the Lagrange inversion. And so let me apply this to the notion, a notion which is very important in free probability, which is called free convolution. And I will show you how to apply this to random matrices then. You take two probability measures on the real line. Now you can compute by some abstract nonsense construction an algebra A and two self-adjoint elements, n and b, which will be free in the algebra A, which means that the algebra generated by small a, the algebra generated by small b will be free in the sense that I mentioned before, and whose distribution will be given by mu and nu. Well, in this case, I should assume that mu and nu have moments of all orders. Then the free convolution of mu and u is a distribution of the sum of A plus B. And this is actually parallel to a well-known construction in classical probability, where instead of taking free random variables, you take independent random variables. When you take their sum, of course, the distribution of the sum is a convolution in a classical sense of the two distributions. But here we have a new operations on probability distribution, which is called the free convolution. Okay. How do you compute the free convolution? Well, you can use the moment generating series, but it is slightly better to use something which is called a resolvent, which is almost the moment generating series, which is g mu of z, which is the integral of 1 over z minus x d mu of z x. So you can expand this in terms of the moments of the measure mu, which are these numbers. I say it's slightly better because you see that in this form, actually it is defined for any probability measure on the real line, as soon as z is a complex number without, I mean, the integral converges as z is a complex number with non-trivial imaginary part. So this defines an analytic function on the upper or the lower half plane. So, and well, you can now invert this function near infinity. And well, in the case where you have moments of all orders, you can see that the inverse of this function near infinity, it looks like 1 over z plus a series with non-negative powers of z. And here's the Rn of the free cumulants of mu. And the theorem, which of course is that these free cumulants, they linearize the free convolution in the sense that the nth free cumulant of mu and nu plus nu, the free convolution, is the sum of the free cumulants. And the proof is one-line proof using that you look at Rn of A plus B, A plus B, A plus B. This is multilinear, so you can expand into to the n terms here. And all terms vanish because they are mixed cumulants, except the two which are here. This is a proof, just one line. But of course, we have done quite a lot of work in order to get to this. Using this, you can prove, for example, the free central limit theorem, the analog of the, if you take x1, x2, xn, a family of freely independent random variables, which are centered and whose variance is equal to sigma squared, then x1 plus x2 plus xn over square root of n. So this has a certain probability distribution, and this probability distribution will converge when n goes to infinity to the semicircle distribution. Moments are given by essentially Catalan numbers, multiples of Catalan. And I mean, this is proved by very easily using actually, this semicircle law is actually characterized by the fact that the K series that I mentioned has only one non-trivial term here. There is always 1 over z term, but here you have z sigma squared, which corresponds to the second cumulant, which is non-zero. All the other cumulants vanish. And actually, it's very analogous to what you get in the classical case, where you look at the Gaussian distribution on the real line, all its cumulants in the classical sense vanish, except the second one, which is given by the variance. Okay, and now I come back to the example that I was, I will come back to the example I was giving at the beginning of my talk yesterday. So let me recall this model of random matrices. L is a diagonal matrix with some given spectrum, D, and I rotate it by some random unitary matrix, choosing this Haar measure. M, same kind of matrix. You choose a spectrum, and then you give the eigenvectors, you choose them at random, using Haar measure. And then, well, for large n, what you have is that the nth cumulant of the sum behaves like it will be very close to the sum of the free cumulants, L and M. And so if we come back to my first example, if you remember, I was trying to compute the spectrum of pi1 plus pi2, where pi1 and pi2 were orthogonal projections on random subspaces of dimension n/2. Okay, so you take a square matrix, you take half of the eigenvalues are equal to 1, the other half is equal to 0. So it's an orthogonal projection. And now you conjugate it with a random unitary. And now if you do the computation with the free cumulants, you can compute this distribution, which is the Bernoulli distribution tells you that here you have half of the eigenvalue which are equal to 0, half of the eigenvalue which are equal to 1. This is the Bernoulli distribution. So delta 0 is a probability distribution which puts the maths 1 at 0 and 0 everywhere. And same similar for delta 1. So this you can compute using what I said about free cumulants. And what you get is the arc-sine distribution. And actually, you can check all this on the computer experiment, as I said yesterday. Here I have 800 matrices, and I checked that the distribution of eigenvalues, and if you want to have fun, you can do it with your computer system for making random matrices. Okay. Now, I want to explain how free cumulants arise from matrix integrals. So the theory that I explained was found by Roland Speicher about 30 years ago. Okay, so he made some observation that he had a free central limit theorem, and in the free central limit theorem, he saw that the Catalan numbers, they count non-crossing partition with two non-crossing partition into pairs. And he knew about the theory of cumulants by Rota and Combinatorics. And he had the idea that you can use non-crossing partition to define cumulants, and these will be very well fitted to this free probability. So it was some inspiration. Okay, so but if you want to do that, you have to be clever. I will show you how to do it. If you are not clever, but you know a lot of things. So but of course, this is much later that we can come to that. Okay, so let me take A1, A2, AP, and B1, B2, BP being n by n matrices. Okay, and U, a random R unitary operator of the same size as these matrices. And let me take A1, A2, AP's small a elements which are free with B1, BP, and such that they have the same moments as the matrices which are on the left. But here I have the big A and big B, they are matrices of finite dimension. The A and the B, there are some abstract operators in some operator algebra, which I don't really want to introduce here. I just say that this kind of thing exists. You can prove it by abstract nonsense. So what we would like to do is to prove that for large n, the quantity which is here is very well approximated by the quantity which is below here. Which means that the A1, A2, AP, and the UB1 U star, UB2 U star, UBP U star, they behave like A1 AP and B1 BP. Of course, if I don't have B1 BP, it's trivial because it is in my hypothesis. Same thing for the B's. But of course, if you put them together, then you have something non-trivial which happens. The position of the A's and the B's becomes something very specific in the, like I said yesterday, when you take n vectors at random in a very large dimensional space, they become orthogonal. And here, these two sets of matrices, they position, each of them is fixed by these numbers, but the relative position of the A's and the B's will, in some sense, be determined by all these numbers. And these numbers, they are determined by the fact that the A's and the B's are free. And I've shown you just a few minutes ago a formula for that. So we want to recover this formula. Of course, this formula I showed you, for example, you have this expression where the three cumulants occur. So there is really something with the three cumulants here, and we want to recover this formula by understanding random matrices. For doing that, we will use a basic fact about representation theory, which is the Schur-Weyl duality. So it's a vast subject. I show you only the simplest case of the Schur-Weyl duality. So you take a space of dimension big N, which will be, if you want, the space on which my matrices will act, and take the tensor product of V by itself Q times. Then the group, the symmetric group SQ, it acts by permuting the entries of the tensor product in this way. Okay? So if you have a tensor product, you just exchange the elements in the product. And we have also an action of the group U of N diagonally. It acts on each of the vectors. And well, the two actions commute. This is quite obvious. What is less obvious is that each action generates the commutant of the other. So really, if you look at the algebra generated by the action of U and the algebra generated by the action of sigma, these are commuting. Each algebra is a commutant of the other. And this is, of course, less easy to see than just the fact that the two actions commute. It means that you have enough. If you want to, for example, to find the commutant of this action here, this tells you that it is enough to consider these operators, and by taking products and sums and so on, you can generate everything, the commutant. Okay, so now let me take A1, A2, AQ matrices, and for a permutation sigma in SQ, I call trace of sigma and the sigma of A. So here, for a moment, I will use a big T because I don't want to keep 1 over n everywhere in my formula. So, but come back to the small trace. I take the product over all the cycles of sigma of AI, A sigma of I, A sigma square of I, etc. So you take one element in the cycle and you iterate sigma. And of course, this doesn't depend on I because in the cycle because of the cyclicity property of the trace. So you take a product over all cycles of sigma. And now the Schur-Weyl duality, well, if you think about it, this implies that this quantity, in which I integrate over U, obviously it is, if you think of this expression in terms of the coefficients of A and the A's and the B's, it is a polynomial. It is of degree 1 in each of the matrices A's, of degree 1 in each of the matrices B. And actually, it can be expressed in terms of the quantities trace sigma of A and trace rho of B, where sigma and rho are in the symmetric group. Okay. There is, I mean, this follows, but I won't give you the proof, but this essentially follows from the Schur-Weyl duality that you can express such a quantity, because essentially what you do when you are integrating over U's is that you are rendering your quantity invariant on the, so it commutes in some sense with the action of U on your space. So it should belong to the commutant which is given by the action of the symmetric group. And these quantities are obtained by letting the symmetric group act on the. So this is not a proof, of course, it's just an explanation of why you would expect these quantities to rise. But there is a precise formula. And the precise formula is the following one. It's precise except that I say that it's the sum of the sigma and rho of this, trace sigma of A, trace rho minus 1 sigma of B. And here we have a function, the Weingarten function, sigma 1 of sigma 1 rho, and n. So it's a function which depends on the big N, which is the dimension of the space of the matrices, and which depends on an element. So it's a function of the symmetric group, which depends on this element N. So maybe a few words about this function. So if you want to compute this kind of integral, so if you expand, so you want to integrate with respect to u, which is the hard measure of the symmetric group. If you expand into coefficients, then you will have to compute this kind of integrals. Okay? An integral of a certain monomial into the coefficients of the symmetric group in some basis. Okay? Now, using invariance of du by multiplication diagonal, of course, this will be 0 in general unless q is equal to q prime here. And we can see even more using Schur-Weyl duality. We can see that this integral will be 0 unless I prime 1, I prime q is a permutation of I1, IQ, and g prime 1, g prime 2 is a permutation of g1, gq. And actually, the Weingarten function arises when you compute this integral, where you take element I1, IQ. So here, for convenience, I take I1, IQ to be distinct, because if there is some repetition, the formula is slightly more complicated. But essentially, this function arises when you do this integral, where I1, IQ are distinct integrals, G1, GQ are distinct integrals, and you have a permutation pi. So you see I1 in the U bar. So U bar is, of course, it's complex conjugate. So in the U bar, so the J are the same place, but the pi are permuted. Of course, you could of course permute the thing and see that it is the same thing as pi inverse. But essentially, this is what is called the Weingarten function. My student in his studies, he introduced this name, Weingarten function, which since has been used by many people. So it comes back to computation which were done by physicists in the 70s, trying to compute these integrals. He got some formulas, but okay. So what can we say about this function? Wait, it's a non-trivial function. But there is a very simple way of characterizing the function, which is this identity. You take so here we take the sum of all permutation of sigma times t to the length of sigma, the length that we are using here, the absolute length, of course, not the Coxeter length, the absolute length. And of course, this in this sum here, so the absolute length, of course, is invariant under conjugation, which is not the case of the Coxeter. Yes. That's the absolute length. Yes, invariant. It's n is here q minus the number of cycles. And now you take sorry, I forgot to put a sigma here. So it's a generating function of the function Weingarten function, but I forgot to put a sigma here. We put it before I send the slides to Yannick. And now just the product of the two is one in the group algebra of the symmetric group. Okay, these are two elements in the group algebra of the symmetric group. And if you put t equal to 1, then the product is equal. So it's a simple form, but of course you have to do an inversion if you want really to compute the Weingarten function. And if you want to do the inversion, you can do it explicitly using a notion of monotone factorization. I will not explain that today. It was developed as a what? Yes, there was some monotone factorization today, this morning. Yes, but it's not exactly. I don't think it's exactly the same. Yes. You have to invert. It's a kind of. You have there are other formulas for the Weingarten function. For example, using characters of symmetric groups, and you can develop various formulas. But okay, but what is important for us is the asymptotic behavior of the Weingarten function. We don't really need all the value of the Weingarten function, but we see it is deeply related to the length function of the symmetric group. And actually, if you do the analysis, you see that the Weingarten function is at first order. I mean, there is an expansion in terms of negative powers of n. At first order, it is what I call the Möbius function of the symmetric group, which is just the extension. You know the Möbius function of the lattice of non-crossing partition, which is a function which is on permutations, which is invariant, which depends only on the actually it depends only on the what? Yes. Yeah, yes. The cycle length, so it is invariant on the conjugation, so you can extend it to the whole group. And it is given here. Okay, it's essentially a product of Catalan numbers with some sign of the cycles. So here, C as a cycle of sigma. It's not the big cycle. So yeah, I should maybe have used another interpretation. Now, what we do is we use this equation and we replace in this equation we use the asymptotic of the Weingarten function. And if we compare these two formulas, we see that in the end, this quantity, I mean, the integral of the expectation of this quantity is close to this quantity. So now we have seen, coming from the integration of the unitary group, we have seen the free cumulants arise naturally. And we have seen naturally that they arise from the legs function for the absolute order of the symmetric group. So you don't have to be clever, but you have to know a lot of things. Usually, that's okay. So I said when I say this is equal, I mean the integral certainly is close, so the expectation. But I mean you can use the same type of argument to say that the variance goes to 0. So that actually this random variable, when n goes to infinity, is closer and closer to its expectation. So actually this in probability. Okay, so since the invention of free cumulants, now 30 years ago, they have appeared in other problems. So I will mention a few of them in which I was involved, but there are many other places where they have appeared. But I will mention just a few examples from my own work. So the first is the large n limit. So here it's my own work, but it was done by Benoit in his thesis. It was a problem that I asked him to look at. So the large n limit of the Itzigson-Zuber integral, which is a very important integral in random matrix theory. So you take two Hermitian matrices, and you take the integral of the exponential of n times the trace of UA U star times B. In some sense, it's essentially the Fourier transform of the orbit measure on some on the space of Hermitian matrices, in the space of all matrices with a given spectrum. So it's a very well-known integral, which there are explicit formulas for these in terms of determinants, which were devised by Harish Chandra and then rediscovered by Itzigson and Zuber physicists in the 70s. But the explicit formula, from the explicit formula, it's quite difficult to get an idea of the, they are given in terms of quotients of determinants, so it's a bit difficult to get an idea of the asymptotics. And so using this, so there have been several work on that, and what you see is that if you look at the integral, the free cumulants arise naturally from the asymptotic. I will not explain more about that. So very recently, I was contacted by Denis Bernard, a physicist in Paris, who found some nice polynomials, which he called loop polynomials, and they asked me, what are these polynomials? And I thought hard for a few months, and then I found a formula. And 3 weeks after I found the formula, I said, but these are free cumulants. And so the free cumulants appear in this formula. I won't explain more, but I was very surprised because I never expected. I've been working on free cumulants for 30 years, but I never expected them to show up in this problem. It's a bit of a miracle. Since we have heard, I didn't really intend to talk about this, but I mention it now. Since we have heard about braids and Garcite structure, I should mention that I was contacted by Patrick de Hornoy about 10 years ago, a little more than 10 years ago. He had a sequence of numbers, and he asked me, can you find these numbers? You can give me a formula. I looked at these numbers, and after some thought, I said, but these are free cumulants. And so what are these numbers? So the definition is here. It's a number of braids of length at most 2 in the dual braid monoid. So I will not try to explain because I'm not sure I would be able to do that. But this number is a 2n cumulant of a product of classically independent semicircular variables. So why is it true? I mean, it's because you can do the computation, and certainly because probably there is deep relation between non-crossing partitions and the Garcite structure, braid monoid. And actually, it is closely related to a formula, which actually I proved this formula in order to get this as a special case. So if you have x1, xk, a family of independent random variables which commute, and you want to compute the free cumulants of the product, x1, x2, xk, then there is a formula, a nice formula, which tells you that nth cumulant is the sum of all k-tuples of non-crossing partition, whose supremum is the largest partition in the absolute order, of the product of the free cumulants of the here. Okay, so no, these are non-crossing partitions. U1 pi k are non-crossing partitions, but you ask that their supremum is not they are not reducible. Yes, it is a non-crossing join. Yes, sure. Well, if I remember correctly, but yes, I think it's. But of course, it is completely useless because you don't really want to compute free cumulants of a product. I mean, if you have independent random variables and you want to compute the expectation of the product, you don't really have to do all that to get the solution. How much time do I have? 5 minutes. So okay, so let me give as a final example of free cumulants, how they arise in the theory of characters of the symmetric groups. So we know that the reducible representation of the symmetric group are indexed by integer partitions. Okay, so if the symmetric group is given as size n, these are integer partitions of n. And so in my talk, so I present them usually like that. So for example, the partition 4, 3, 1, you can represent as a piecewise linear function like that. So you have, so if you shift it a little bit to the right, you get the French way of representing non-crossing partitions. Yeah, this is Russian. This is Russian. Okay, so you represent this as a piecewise linear function, which is above, which is equal to minus x for large x, or plus x for large x. And between them, it has slopes of either +1 or -1. And there are local minima and local maxima in this function. And from that, you can compute something which is called the transition measure by Kerov. So this transition measure, it is given by some formula, but it's given in terms of the local minima and local maxima of the function. But the formula is not so important. What is important is that this transition measure has a very natural interpretation in terms of the representation of the symmetric group. It represents what happens when you do induction from Sn to Sn plus 1. In some sense, it tells you how much, when you reduce a representation from Sn to Sn plus 1, what you have to do is to add some square, one of these places, and then you get something which has a certain dimension. And now you put a measure which is on these x which are here, which is proportional to the dimension of the induced representation, the specific part. So this measure has moments. So it has well, I said non-crossing. I should say free cumulants because Roland said you should use free cumulants. And now there is a formula for characters of symmetric group. If I look at the characters of symmetric groups evaluated on a cycle of order k, and I multiply it by, so Q here is the size of the symmetric group, and Q indexed by k is a descending factorial of Q. So I normalize the characters in this way. And there exists universal polynomials, and these polynomials actually are independent of Q. This is quite remarkable, such that this quantity, so it should be, sorry, I should put k here, it's a sigma. It's k like k of mathematically. I mean sigma. So sigma is a polynomial in the free cumulants of the measure. And these free cumulants are, so these polynomials, I give some examples here. So this one is R2, then R3, then R4 plus R2, then R5 plus 5, 3. And then a few more examples. And actually, it was proved by Maciej Jolenga, Valentin Ferret, and Piotr Sniadi that these coefficients have non-negative integers, and they count actually some objects in the symmetric group, some factorization in the symmetric group. I won't explain exactly what factorization, but they count really things in the symmetric group, really all these. The ones here, but the 15, the 5, the 8, and so on. You can give them concrete, very concrete. And one important thing is that if you look at the term which is linear, which is of degree 1 in the R variables, so R2, R3, R4, R5, 6, R7, it's linear and it's of highest degree if I call by degree the product of the indices. So the degree here is 6, 4 here, 4 here, and 2 here. And if you look at the time of highest degree in terms of the index, it's always linear, and the coefficient is 1. And actually, this goes back to what I proved quite a long time ago, that when n goes to infinity, the normalized characters of the symmetric group, they factorize asymptotically. That is, if I take sigma 1, sigma 2 small permutations with disjoint supports, then the product of the characters of the product is essentially like the product of the characters with some error. And actually, so if you have this, then you see that you can always, if you have some permutation, sigma, you can expand it in a product of cycles, and then you have a product of these terms, which are free cumulants. Okay, so really, in the asymptotic of characters of symmetric group, you see product of free cumulants over the cycles of the permutation, which appear in some asymptotic range. And as a consequence, free probability governs the asymptotic behavior of representation of large symmetric groups, which is something quite remarkable. And then I will stop here for the day. Thank you.